All right, hello class. So in this video, we're going to continue looking at theorem 2.3.3. So we are still in section 2.3, of course. And last time we proved part A and part B. So today we're going to try and get through part C and part D and see if we can prove those. All right, so let's look at the proof of B, or sorry, of C. Okay, so we want to show that the limit of an times bn converges to a times b, and that's provided, of course, that an converges to a and bn converges to b. Okay, so we're going to start by letting epsilon be greater than 0. So let epsilon be greater than 0. And I'm just going to say we wish to find an n such that the absolute value of an times bn minus a times b is less than epsilon for all little n greater than or equal to big N. All right, so here's where we're going to use quite a bit of what we've already established so far. Okay, so first of all, what I'm going to do is I'm going to use that funky version of 0. I'm going to find something to add and subtract on the inside here. Okay, and there are, a couple ways we could do this, but I'm going to add and subtract by the same thing. So note that the absolute value of a and bn minus ab is equal to the absolute value of a and bn. And from here, I'm going to subtract, let's do abn and then add abn on the inside, and then apply the triangle inequality. Okay, so this is triangle inequality with this setup here. All right, and all we're doing is we're adding and subtracting this abn plus, the abn. Okay. Now we have some algebra we can do. Here we can factor out a bn. And we'll be left with an minus a, absolute value. And here we can just factor out the a and get bn minus b, absolute value. All right, so we want this less than epsilon. But we already know that these two guys here, this an minus a and this bn minus b, those distances, we know we can get them as small as we want since we have convergence. An converges to a and bn converges to b, so we can essentially get these as small as we want. Okay, so, and then here, this bn, well, we're going to have to deal with that. So here's what I would like. And here's my first stab at it. Here's what I'd like. I'd like, let's say an minus a less than epsilon over bn. Well, okay, so that would cancel with the bn, but unfortunately we don't usually like to have things that vary underneath the epsilon, so we'll have to kind of go back to the drawing board here, And then here, we'd also like this bn minus b may be less than epsilon over the absolute value of a. Okay, so it would cancel with that. So I'm looking for things that will cancel. But I have another problem here. If this is 0, if a is 0, this is a big problem. Okay, so there's a couple of things we're going to need to deal with. Okay, so let's approach those. Okay, so I'm going to call this statement here star, that a and bn minus ab is less than or equal to this. All right, so we'll come back to that. Now, since an converges to a and bn converges to b, we can say a lot of different things. Okay, for example, there exists an n1 such that the absolute value of an minus a, actually let me do this first. Since an converges to a and bn converges to b, well, since bn converges, then the sequence bn is bounded. And this is thanks to, by theorem 2.3.2. So there exists, say, a capital M greater than 0 such that the absolute value of bn is less than or equal to this capital M. All right, so further, there exists an n1, so now we'll do this part. There exists an n1 such that the absolute value of an minus a is less than whatever we want. So I'm going to say it's less than epsilon over 2 times m, because this, and the reason I chose that, it's because I know that my bn's are less than or equal to m, and I want this m to cancel, and I want just like an epsilon over 2 here. All right, so what I want here is less than epsilon over 2. Okay, so if that's what I want, let me move this over here. I want capital M times the an minus a less than epsilon over 2, because I want this less than epsilon over 2 and this less than epsilon over 2. Okay, so I just move the m over, and we have it. Okay, so that's where this comes from. And I know I can do this because we have convergence, and that means I can make this as small as I want. So, all right, we're good to go there. Now, the next part, and this is, of course, for n greater than or equal to this capital N sub 1. Okay, and there exists an n sub 2 such that bn minus b absolute value is less than epsilon over 2 times the absolute value of a plus 1 for n greater than or equal to n2. Okay, so where did that come from? Well, for this piece, I wanted this less than epsilon over 2 as well. So if I go over to my scratch work, right, I want absolute value of a times absolute value of bn minus b less than epsilon over 2. If I move this a over, I'll get this. However, this is a problem if a is 0. Okay, so to mitigate that, that's why I put in the plus 1 here. So I'm not dividing by 0. All right, now, and I'll show you in a minute why that works out okay. All right, so I just need to make sure I'm not dividing by 0 here. All right, and I don't want to break it into cases. You could, but I don't want to. All right, now letting capital N be the maximum of N1 and N2. So this is exactly like we did last time. Okay, we'll get that all right, we'll get star becomes, all right, so I'm leaving part of it up here, but it's this a n bn minus a times b, and we already by star got this, which was the absolute value of bn times an minus a, plus absolute value of a times bn minus b. Okay, now this bn is less than or equal to m, since it's bounded. I'm not really messing with anything else here. Okay, now I'm going to start putting my pieces in. So this an minus a, well, we have that that's less than epsilon over 2m. Now plus absolute value of a times, and next we'll do this. We got the bn minus b is less than this epsilon over 2 times absolute value of a plus 1. So this will be all over epsilon over 2 times absolute value of a plus 1. Okay, now absolute value of a over absolute value of a plus 1 is less than 1 because the denominator is 1 greater than this one. Okay, so this whole thing is, well, the absolute value of a and absolute value of a plus 1 ends up being less than 1. So here the m's cancel. And here it's not so much that the a's cancel, it's that these together are less than 1. So we get that this whole thing is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. And there we have it, implying, and I should really say, sorry, this is for little n greater than or equal to our capital N. We do need to specify that. Okay, so an bn converges to a times b, and there we go. All right, so notice that this one maybe feels a little sloppier than the other ones we've done so far, and it's when we got to here that I needed to piece something together. Okay, and notice I had to use an extra theorem. Had to use that these bn's were bounded. Okay, and then that is how I set up its little epsilon thingy. Now notice I didn't have to put a plus 1 here for the m because I specifically chose m to be positive, which the only way m would be equal to 0 if this was just a sequence of zeros, and if that was a sequence of zeros, well then it could be bounded by any positive number you would want. All right, pick one. So yeah, I know that the first time you see these, it's kind of mind-melting, but remember what we're trying to do is we're trying to get the guy we're looking for, this distance, to be less than epsilon. And we do that by getting it into terms of things that we know we can get them as small as we want, right? We know we can get this guy as small as we want, and this guy as small as we want, and we know that this guy is bounded, so we can actually work on that too and get all of them together in such a way that we can get the whole thing less than epsilon. All right, so let's try and prove the last part of this, the division part. And actually, we can just use part C provided. So for the proof of D, it's actually a little easier than it looks, because we don't actually have to reinvent the wheel here. So we can apply part C by basically using that AN times 1 over BN converges to A times 1 over B. However, there's one little thing, and we can use this using this if we can prove that Bn converges to B implies 1 over Bn converges to 1 over B, provided that B does not equal 0. Okay, so really we can just prove this, that 1 over Bn converges to B. If we can do that, then we can just apply part C to get the division part in general. All right, so this is what we're going to focus on proving. All right, so to do that, what we want to do, all right, so we let epsilon be greater than 0, and we wish to find an n such that 1 over Bn minus 1 over B absolute value is less than epsilon for all little n greater than or equal to this n that we've found. Okay, so to do that, let's play with this a little bit. We know that 1 over Bn minus 1 over B, we'll do the fraction arithmetic here and get this will be B minus Bn all over B times Bn. Okay, also known as, we can sort of adjust this a little bit. This will be the absolute value of Bn minus B, and this will be B times Bn. Okay, so, and this is what we want less than epsilon, and this is tricky. Now we can get this Bn minus B absolute value, since we have convergence, this part can get as small as we want. It's this denominator that's going to give us some issue. Okay, so let's see what we can do about this. Let's have a thought. All right, so one thing we need to make sure is that we don't want to be dividing by 0. Okay, now we know B is not equal to 0, right? However, Bn may be. Okay, so B, for example, may be up here at, I don't know, 1. And then some of my bn's may be at 0, like b10 might be here at 0, and b11, and then it might jump up here, and eventually, you know, all my b's should be away from 0, but some of them may still be 0. So we want to make sure that we pick values greater than 0. So we need our n to be such that bn never equals 0, which shouldn't be too difficult because we know that, you know, it's not converging to 0, so at some point it has to be further away. So if we think about the number line here, let's say this is 0, and this is absolute value of b. That's what I actually have here. So if I choose epsilon, say here, right, if I choose epsilon to say be the half the distance between b and 0, so absolute value of b over 2. Okay, so this is my epsilon. So this is absolute value of b plus epsilon, absolute value of b minus epsilon. So there exists an n. So let me write this. Since bn converges to b, right, there exists a capital N such that the absolute value of bn minus b is less than the absolute value of b halves. Okay, so in other words, for all n, for all little n greater than this big N, all of my terms should be in here, and that should make them positive if I'm looking at the absolute values. Okay. All right, so let me write that out a little bit. So this is for all little n greater than our big N. Okay. Now, if all my little terms, all my absolute value of bn's are in here, then they're all greater than b minus epsilon. So now I didn't really specify it here, but here we are letting epsilon be absolute value of b over 2. Okay, so this implies that for all n greater than or equal to capital N, that absolute value of bn is greater than the absolute value of b minus epsilon, which is going to be absolute value of b over 2, because if we subtract absolute value of b over 2 from absolute value of b, we get absolute value of b over 2. Now, what does this mean? Well, this is positive, and if we flip this fraction over, we get that 1 over the absolute value of bn is less than 2 over the absolute value of b for n greater than or equal to this capital N. Okay, so that can help us here, because this can give us that the absolute value of bn minus b over the absolute value of b over the absolute value of bn, well, that this piece here I can say is less than, it will be 2 times the absolute value of bn minus b all over absolute value of b times absolute value of b. And I think we're in business now because I want this less than epsilon. Okay, so that means if I move some things around, that means we want the absolute value of bn minus b less than epsilon times the absolute value of b squared all over 2. Okay, so what I'm going to do is I'm going to call this guy n1. I should have done that to begin with. Okay, so now since Bn converges to B, there exists an N2 such that the absolute value of Bn minus B is less than this epsilon times B squared over 2 for all n greater than or equal to N2. Now, letting capital N be the maximum of N1 and N2, for little n greater than or equal to this capital N, we'll have, okay, and I'm going to write it out, that 1 over Bn minus 1 over B will be, I'll just jump to it. It'll be absolute value of Bn minus B all over absolute value of B times absolute value of Bn. This will be less than or equal to 2 times the absolute value of Bn minus B all over the absolute value of B squared. So this step comes from this part here. So that comes from, I'll call this star. So this statement comes from star. Okay, then this whole thing is going to be less than, right, 2 over B squared absolute value, okay, times epsilon times B squared absolute value all over 2. I guess I don't have to do the absolute value if I'm squaring, but in any case, these will all cancel, and this will equal epsilon. Now this statement came from this piece. All right, so I'll call this part heart, and so this came to us from the heart step. Okay, so we had a step where we had to make sure that the Bn's were greater than 0, or were not equal to 0, and then we had to take another step to get the Bn minus B small enough to get it less than something that will cancel this stuff. Okay, so first we had to go out far enough so that the Bn's were not ever going to be 0 again, and we had to get out far enough to where this Bn minus B was small enough. So we had to do both in this particular example. Okay, so now that we have this thing less than epsilon, this implies that 1 over Bn converges to 1 over B. And that completes the proof and all of the parts of the algebraic limit theorem. Whew. Okay. So, there's not much left of this section. However, you may have thought that maybe there's a bit easier way to talk about this whole thing, like, you know, oh, if the limit is positive, does that mean after a certain point all the terms are positive, so on and so forth. So this section also details some order theorems. So let's take a look at that. Okay, so I wanted to remind you what we have finished here. Okay, so up next here is the order limit theorem. And as you might expect, it deals with orderings. Okay, so we're going to assume that the sequence AN converges to A and BN converges to B. So here's part A. If AN is greater than or equal to 0 for all n in the naturals, then the limit A is greater than or equal to 0. Okay, so basically if all your terms are non-negative for all n, then what this theorem is saying is that there's no way that suddenly the limit could be negative. Now, keep in mind, this does, if you think about it here, 1 over n is always greater than or equal to 0, but it converges to 0, even though specifically every 1 over n is strictly greater than 0. Okay, but this scenario here still satisfies this because every an here would be greater than or equal to 0. It just happens to be greater than, and the limit A is 0. Okay, so what this is saying is that you can't have a situation like this and then suddenly your limit is like -1. Okay. Similar here, if an is less than or equal to bn for all n in the naturals, then a is less than or equal to b. Okay, so basically if the terms of one sequence always live below the terms of another one, then the limits of those need to satisfy the same behavior. And this one, it looks a little cumbersome, but what it's basically saying is that if C, let's say, is a lower bound of all of the bn's, then C has to be a lower bound of the limit. Okay, it has to be lower than the limit. And similarly, this is basically saying the same thing. Just if an lives below C for all n, then A must also live below C. So, in other words, limits preserve order. Right? They preserve inequalities in situations like this. So let's prove this. Okay, it's really going to be a matter of proving part A because part B and C just sort of follow directly from A, and C follows directly from A and B. So for the proof of A, okay. Let's suppose to the contrary. That A is actually negative, right? So suppose we have a sequence of non-negative values that somehow converges to a negative A. Okay, now we know since AN converges to A, right, there exists an N such that the absolute value of AN minus A is less than really anything we want, as long as it's a positive real number. So we can choose any epsilon. So there exists an N such that this absolute value of AN minus A is, let's say, less than the absolute value of A for all n greater than or equal to this capital N. Now here's why I want to do that, right? This is the epsilon I'm choosing. So if I were to look at a graph, and remember we are assuming here's 0, we're assuming that A is less than 0. Okay. Now, when I let epsilon be the absolute value of A, then when I set up my epsilon neighborhood, right, V epsilon about A, well, that's going to be the open interval of A minus epsilon to A plus epsilon. Well, that's going to be a minus the absolute value of a, and then a plus the absolute value of a. Well, a plus the absolute value of a, well, remember, a is negative, so a plus its absolute value, that's going to go to 0. So really, this ends up being the interval a minus the absolute value of a. Okay, so that would actually be 2a. And then the other side would be 0. So it's really just going to be the interval 2a to 0. All right, and every, since a(n) converges to a, every term past n has to be in this epsilon neighborhood. So I don't know where it lives, but say a(n) has to be here, then a(n plus 1) has to be here, and like a(n plus 2) has to be here, and then all my a(n)s live in this interval somewhere. I don't know where, but somewhere. But specifically, a of capital N lives in this interval. So this implies that a of capital N is in this epsilon neighborhood around a, which also implies that my a(n) is less than 0. And this is the contradiction. This is a contradiction since by hypothesis a(n) is greater than or equal to 0 for all n in the naturals, and we just found that not only is a capital N less than 0, every a(n) past it has to be less than 0 because it has to be in this epsilon neighborhood here. Okay, so this is a contradiction. Therefore, a must be greater than or equal to 0. And there we go. Now, what this gives us, I want to mention this too. We inadvertently proved something else here. So notice, we inadvertently, I have no idea how to spell that, inadvertently proved that if a is negative, then there exists an n such that a(n) is negative for all little n greater than this capital N, greater than or equal to this capital N. Okay? In other words, there are an infinite number of negative terms in this sequence. Okay, and it works the other way. Similarly, if a is positive, then there exists an n such that all the a(n)s are greater than 0 for all n greater than or equal to this capital N. Now notice, it's not that every a(n) is positive if a is positive, just every one of them past a certain point has to be positive. So we actually got this sort of from the proof of this part A, and we kind of saw something similar in the last theorem that we were proving. Okay. All right, so now let's look at part B. Okay, so for part B, actually, we can just apply part A. So for the proof of part B, let Sn be the sequence Bn minus An, which will be greater than or equal to 0 for all n in the naturals. By part A, Sn, by part A, S, sorry, let me say this instead. By the last theorem, by the algebraic limit theorem, Sn, which is equal to Bn minus An, converges to B minus A, right? So that's what I need first. Then, all right, by part A, the limit of Sn, which is B minus A, must be greater than or equal to 0. So B minus A is greater than or equal to 0, implying that B is greater than or equal to A, which is what we wanted. Okay. We can do something very similar for part C. Okay, for part C, let's let T sub n be the sequence B sub n minus C. Okay, which by the algebraic limit theorem, Bn minus C converges to B minus C, and Bn minus C, and let me write it like this, and Tn, which is equal to Bn minus C, will be greater than or equal to 0 for all n in the naturals. So B minus C must also be greater than or equal to 0, which implies that B is greater than or equal to C. Or if we wanted to prove the next part with the A's, I'll show you the other way. So here with the A's, we have the ANs are less than C. So let Cn be the sequence C for all n in the naturals. Okay, then An is less than Cn for all n in the naturals, implying that A is less than C by part B, and since Cn converges to C, right? Just C over and over again has to converge to C. So this is another way you could do it, is by using part B instead of part A. So this would be by part A. Okay, either way, you're just using the previous parts. What I want to mention here is notice how I'm not trying to prove these next parts from scratch. I'm actually letting part A do all the heavy lifting for me, and then in part C I have even less heavy lifting to do. Okay, so always be on the lookout when you're trying to prove stuff. Especially if a theorem has parts, see if you can use the previous part, because a lot of times you could just cite that and get it as a corollary. Okay, so that about does it for this section. So hopefully that can get you started on the assignment, and I will catch you all in the next one. Cheers.